Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We get started. Welcome to the second morning session, Cloud Computing and Chemistry. And our first speaker this morning is Mark Borkum from University of Southampton. Mark?
Great, thanks. Can everyone hear me before I start? Perfect. Oh, the hecklers already, great. Okay, so I'm here to talk about the oreChem project. As the title says, Planning and Enacting Chemistry on the Semantic Web. So just to give a quick overview of the presentation, I'm going to start off with a brief introduction, then I'll talk you through the oreChem ontology, do a quick case study for Xray crystallography, and then talk about the future work that we have planned for the project. So what is oreChem all about? It's about the scientific method. So the little smart art graphic that I've got on the screen gives a summary of the scientific method from my perspective. It's probably worth noting that I'm a computer scientist. I cohabitate with chemists. It's an interesting arrangement. But it gives me a unique insight into the work that they do, and it's quite nice actually to come at everything from a different angle and different perspective. So the scientific method, from my perspective, is all about planning and enactment. So planning, you formulate some kind of hypothesis or a strategy for your work. Some people write it down. Hopefully they put that in their lab notebook. Then you enact said plan. You do some analysis on whatever results you might have obtained during that enactment, and then you publish something, typically a paper at a conference. And as everyone's been talking about, this is becoming increasingly data intensive, or data extensive if you're Jeremy Xray. And this is quite interesting how the cycle is actually affecting research. So what's happening now is people will take other people's data and formulate their own new hypotheses and do new experiments with that. So it's just interesting where people are entering this cycle nowadays. So there's a problem, though, and the problem is the data deluge. So I like to do these things in haiku. If you can summarize something in haiku, then it's typically pretty good. So lots of producers generating more data than ever before. Just an example of that, in Xray crystallography, 40 years ago, a PhD student would generate 3 structures over the course of their entire study. Nowadays, I know people who can generate 10 structures in a day. So it's more than exponential growth in terms of what people can do. So this is the goal everyone talks about. So you want a kind of graph of linked data, or you want the semantic web. So we've got resources in this graph like experiments and measurements and documents, and they're all linked together, and there are scientists thrown in for good measure because apparently they do the work. But this isn't always achievable. And the reason for this is the provenance. Provenance is the lineage or the pedigree of the data. It gives you an impression as to why that data might exist. It gives you the context that allows you to interpret that data. And as Carol Goebel said in her musings on provenance, there are 7 W's, or 6 W's and an H, depending on how you look at it. I've tried to arrange these things in a nice little pyramid structure. So what we've got is the who, so the authors. This is very important. And we've also got this notion of the enactment, so what and how. And these things are very commonplace on the internet. You will find people publishing provenance about who done it and what they've done. Unfortunately, things are missing, typically the annotations, so where they did the work, when they did the work. Timestamps are incredibly important, but often missing. And the biggest one that's often ignored, as I put here, is the why, the plans. So why does the data exist? This is a critical question that we'd like to ask, but we can't answer at the moment. So enter the oreChem project, funded generously by Microsoft Research. And the goal of the project is to investigate what infrastructure would need to be put in place in order to enable people to ask these questions about the why. So I've tried to just label this diagram with the relevant ontologies. So oreChem is going to describe the planning and enactment, so why the data exists, what data is there. And then we're going to use other ontologies to talk about authorship and to do annotations. So just as a few examples, we've got Dublin core, friend of a friend, geonames for describing the geolocation of data, owl time for timestamps and for time spans, which is increasingly important. Right. So now I'm just going to give a quick introduction to the ontology. This is a UML class diagram that describes the oreChem core ontology. So the idea is that the ontology distinguishes between two types of thing, a planned thing and a run thing. A planned thing is something that is going to be realized in the future. So you plan something and then you enact that thing that you've just planned. And a run thing is a kind of retrospective description. I've just done this. So what we've got as the planned things is the plan, which acts as a nice container. It's a document. We can get a URI for it. We can share the links, and people can look at my plans, and hope maybe we'll integrate that with my experiment one day. And then we have the runs at the bottom. And as I said, a run is this realized version of a plan. And I'm going to talk about realization in a bit. So planning, as I've said, is prospective provenance. It's things that will be enacted in the future. It's data that will come into existence. What we're doing is describing the requirements for our experiment. So I've got a small example here for measuring the pH of a specimen of a substance that's in a solution. So the idea is that we break down this workflow or protocol or methodology or whatever nomenclature you'd like to use into a series of smaller stages. And each stage can have as input or output these data products, which are descriptions of things that may be digital or might exist in the real world. So here we've got 3 objects at the bottom, one representing a vial of a solution that will exist, one representing a sample of the solution, and as you can see, we've got at the top this take sample box that requires the big beaker and gives out as an output or emits a small test tube of the solution. And then we've got another one for a measurement, and it says, well, in the future, we're going to have a pH value. And the benefit of doing this is that we can describe each small resource. We can say, well, what is a pH value? Well, it's this term in that ontology. And these kind of requirements are very useful to capture and to share. If I gave this to a scientist, and with the relevant tools, which I'll get onto in a bit, they can fully understand what I mean when I'm talking about measuring the pH of some specimen. So the enactment is your retrospective provenance. So once we've described what we're going to do, we can now describe what we've done. And so what we've got now are 2 stages. I've just called them S0 and S1. So you can tell I'm a computer scientist because I start at 0. And we've got some descriptions of a real beaker that now exists, a real test tube of a specimen that now exists, and a value. It turns out we were measuring the pH of pure water. Okay, great. So one of the things you might notice are the dashed lines between the different boxes. And these are causal relationships which we can infer from the relationships between the stages and the objects. So 2 examples of the causal relationships are the followed relationship, which says that this stage had to have occurred after that stage. It's quite easy to infer because if you look at S0 and S1, the output of S0 has been used by S1. The other causal relationship that we have is called derived from, and that's to indicate that the input, so for the example S0, the inputs have had some effect on the outputs. And so it's possible to create a chain of provenance assertions, and we can work our way back from the data value all the way back to the sample, all the way back to the bucket that we took the sample from. But there's an issue. And this quote, it's always attributed to Yogi Berra, but I can't actually find a proper citation for it, so I'm just going to say unknown. In theory, there's no difference between theory and practice, but in practice there is. And this is especially true in science. You never do what you say you're going to do. Unfortunately, we live in the OWL universe, so everything is the semantic web. And the problem with not doing what you say you're going to do is that the assertions that you make often turn out to be inconsistent. So if you've ever used the protege editor, everything just turns red, and it's very frustrating. So what we wanted to do is, instead of having this notion of instantiation, which is where you say, well, let's say I have a car class, I then have an instance of the car. That's very good until you might change your plan and use a different car. What we have instead is realization. We're saying, well, I'm going to describe a car that's yet to exist, and I'm going to describe a car that does actually exist in reality, and I'm going to link the two together. The main advantage of doing that is that you can deviate from the plan, and Protégé and all other OWL reasoners won't grumble at you. So what we've got here are the two diagrams describing the measurement of a pH, and we're showing the links from the realizations back to the plan. So it's very clear, well, I hope it's very clear, that you can follow each individual data product back to the methodology that was the reason why it exists. Okay, so time for a case study in Xray crystallography. And so I just thought I'd introduce the current practice in Xray crystallography. The data that is produced is very, very highly structured. It's a great field for producing data. They know exactly what they want their files to say, and there are very good standards to say these things. The de facto standard is called the Crystallographic Information File, or the CIF file. And there was a recent report published by JISC, who are a body in the UK, and they were really very keen to promote the CIF file in crystallography. And there's a whole section of this report dedicated to the use of CIFs, which is quite good. The only problem there is that relatively few crystal structures or CIF files are openly available. So this is one of the main drawbacks to not having openly available data, is that you have the possibility for fraud. There have been some very highly publicized cases. The one on the right is particularly relevant. Mr. Murphy decided to publish structures that were unfeasible and couldn't actually be reproduced by the review panel. The only problem there was that because he didn't publish his raw data, and because no one bothered to check or ask for his raw data, people were citing him, and in the end there were about 200 derivative works which have all been invalidated now, purely because there was fraud discovered at the root. So if we could provide an ontology or any other mechanism that could create these causal relationships and allow people to search them, then fraud could be detected earlier, and all of this horrible situation could be avoided. So enter the eCrystals Federation, which is another JISC project, and the goal of the project is to create a network of crystallography resources. The great thing about eCrystals is all of the published records, and I want to emphasize published, so records can be embargoed and often are, but as soon as the record becomes public and openly available, all the data is made available as open data. And open data is in capital letters because there are certain requirements that are mandated for you to have the open data badge appear on your website. One of them is that all of the data files must be persisted over time. And this is incredibly important. It's also important to note that eCrystals is based on ePrints, which is great software because it's extensible. And I'll talk more about that in a second. So just to give you an example of an eCrystals record, each record has a lot of metadata. It's highly structured. There's bibliographic metadata, so the authorship and the when, so lots of timestamps. There's the fundamental and derived data. And the idea there is that everything is provided so that you can perform your own validation and verification of the final result. And of course, as I've got there, the final structure solution is also provided. And if you can see on the screenshot, I know it's a bit small, sorry about that, but there's actually a JMOL rendering of the CIF file that is produced as the final solution. So how did they actually get there? Bear in mind, I'm not a chemist or a crystallographer. This is a very high-level description of what they're doing. They take a powder specimen of a substance, they bombard it with X-rays, they measure the angles for the diffraction, so X-ray hits the structure and bounces off somewhere. They compute the electron densities, and then by some serendipity, and a guy called Pete, in the case of eCrystals, they arrive at a crystal structure solution. The diagram, though, on the right of the slide is taken from the original eCrystals paper. So this is actually quite important. They did have an idea of what their workflow actually was, but after a lot of consultation, it turns out that what they thought they were doing and what they were actually doing were two very different things. So what we did as the oreChem project is we decided to construct a plan, or an oreChem plan, to describe their methodology. And as I said before, the plan contains the requirements. In this case, it's the requirements for the software and the data products that are produced. So we've got, they use many specialist applications and data files, and the plan allows you to say, use this application to turn that file into this one. And it goes on and on and on, and what we end up with is a very nice causal relationship running down the diagram. And so we can see, oh, they're going to start with some raw data, and they're going to end up with a fully finalized structure solution. So each of these is then turned into an oreChem run. So a run is a description of a realization of a plan. In this case, for eCrystals, each eCrystal, each record in the repository, is turned into an oreChem run document. That's RDF XML. What you're looking at in the diagram is actually using XSL to turn that document into something that looks more like a web page. We have found that the clients for eCrystals don't like looking at RDF data. They much prefer HTML and tables. We use Swirl, the Semantic Web rule language, to infer the causal relationships. And this run describes the software that was used and the data files that were produced. And this is really important. And the diagram actually that's shown in the slide, we found that the eCrystals clients are very appreciative. When we give them these diagrams, they know exactly what files have been produced and how. So how did we actually arrive at these diagrams? What we've got, to start off with, we have the full, this is on the left, I should say, we have the full breakdown of the run. So there's stages, which are the rectangles, and objects, which are the ellipses. The stages represent software applications, the ellipses, the data products. And we've got two relationships shown with solid and dashed edges. So the dashed ones are the used relationship, or has as input, and the solid arrows are emitted, or has as output. And then we do a bit of swirl on this in order to arrive at the diagram on the right. So now that I've told you that, you can probably see how it works, but for those who can't, let's just show you the swirl rule quickly. So what we're saying in the swirl rule is if a stage uses an object and emits another object, then there's got to be some causal relationship between those two objects. And so just as an example, here's XPrep, which is an application that they use. And what we're going to do is apply the swirl rule, and we get this nice causal relationship. So we can say that the files are derived from each other. And the derived from tree is actually placed on the eCrystals website. Customers don't really care what software is used. They just want to know what files are available. This is just an interesting outcome. So what kind of things can we do now? And this is going back to the crystallography and fraud idea. Well, we can start doing SPARQL queries. We can start asking intelligent questions. I realize SPARQL isn't very exciting to read, so here's a pictorial version. What we're doing with this query is we're asking for, get me the raw data, the reported result, and everything in between. And the nice thing about using oreChem is that we can essentially link our query to the methodology, to the plan. We can say, well, the raw data is the realization of, in this case, an HKL file. An HKL file, if anyone's seen the front cover of Gödel Escher Bach, you've got the H, K, and L dimensions, and that's basically it. The CIF file is the crystallographic information file, and they're both contained in this eCrystals plan. And so the result of this query is, just for the example record eCrystal 20, we have the oreChem run, we've got the raw data, we've got the reported result, and we have everything in between. And so this is incredibly powerful, because now for every record we can say, well, here are all the data products that you, the review panel, need to look at in order to verify and validate this work. And so just to show you everything all together, this would be the result if you executed the SPARQL query. These are the bindings that you'd get back. So there are 3 results, and they would make 3 rows or 3 sets of bindings in the SPARQL results. Okay, so just to summarize and give you an idea of the future work, we want to expand on the core ontology. One of the things that we haven't looked at yet is the notion of branching and conditional structures. So it is possible that you'll want to ask the enactor a question in a hypothetical sense, and say, which path in the methodology should I follow given everything that I've already done. And the other idea that we want to pursue is something called continuations. This is particularly important. How does one represent a set of data points? Steve is smiling over there. So Steve's laser experiment produces thousands of data points. And RDF, even if you're using the very, very compact serializations of RDF, it becomes incredibly cumbersome to talk about thousands of things in the same document. We've crashed many a web browser. So what we want to be able to do is describe a continuation. We want to say we have this set of points, we have this set of timestamps, you glue them together for me so that it doesn't crash my browser. The next thing that we want to do is have a lower ontology that can be specialized for physical and computational chemistry, so it can bring in terms like software application, script, relationships between them, and specialist resources for chemistry like a sample or a specimen. And finally, we want to talk about, or we want to implement applications and services that use oreChem. So some of the ideas that we've been discussing is having a designer application for the plans so that people have this nice graphical interface that they can work in, and then the idea of an enactor, or a way of simply ingesting the plan and providing the scientist with some kind of interface where they can say what they've done. And this is really important because, as I've said previously, you don't always do what you say you're going to do. And lots of tools that have been produced, I won't name any names, suffer from the issue where if you deviate from the plan, the tool breaks because it's simply incapable of doing something that wasn't previously accounted for. And the last thing that we want to do is have a provenance inspector. So once you've enacted your plan, you want to review the results, you might want to compile a paper to talk about that, or maybe you want to send that provenance information to someone else. So to summarize, here's the summary expressed in XML. And I'd just like to do a few acknowledgements. So thank you very much to Microsoft Research for funding the project. And I've tried to get all the names of project members on there, but I'm sure I've probably missed a few people. So the oreChem project, the PI for the project is Carl Lugosi from Cornell. Southampton are involved, obviously. We've been working with Cambridge. We've been working with Penn State University, with the Lee Giles Group, and with Indiana University, University of Indiana, with Marlon Pierce's group. So thank you very much, and I'd be happy to answer any questions.
Thank you very much, Mark. That was fantastic. Causes me to wonder if we had a plan for the oreChem project. We should have.
Yes.
Maybe we should insist on for all of our future projects.
So your SPARQL slide went by very quickly. I didn't quite follow it. So you need to somehow compute a transitive closure or something.
Yes.
In order to get all the information you wanted there. How do you do that in SPARQL? Is there a recursion capability there, or are you using property paths in SPARQL 1.1, or what are you doing?
How we do at the moment, we're actually implementing the queries. We've got some handcrafted libraries. There is a lot of scope for optimization, though. Once we get access to the query engine, it is possible to bound the queries by these realization relationships between the runs and the plans. I'm just going to plug my laptop in again so I can bring it up on the screen.
So there are facilities coming in SPARQL 1.1, I know, for property paths that allow regular expression on paths, which look like they'd be useful for provenance, but I'm not quite sure how you do it in the current incarnation of SPARQL.
Like I said, at the moment we are implementing these things by hand. It is very, very expensive to do transitive closures. In fact, we actually have to use 2 of them in order to do the query that I showed on the slides. Right, here we go.
And
so, at the moment we are using dig and a combination of dig and pellet to do our queries. So I'm just going to bring it up on the screen. So the red arrows, or the has plan object relationships, are used to bound the queries in order to make the transitive closures a little more efficient to compute.
Time for one more question. Hugo, you want to come up? Nope. Okay. Thank you very much. Let's give Mark another hand. the...
lost my connection.
There you go. Second speaker in the session this morning is Hugo Hiden from Newcastle University, who's going to be talking on accelerating chemical property prediction with cloud computing, furnishing us with the cloud in the session title.
This is all. Excuse me a second, let's get this. I thought these were supposed to just work. Right. What I'm going to talk about is some work we did earlier this year with some people in the Cancer Research Institute at Newcastle University. And what we were doing is trying to make use of cloud computing, Windows Azure, to speed up the process of building predictive models of chemicals. It was funded by Microsoft, who generously provided us with the Azure resource and also some of the salaries. I was involved with the implementation side in computing science. And it was very much led technically by the Institute for Cancer Research, who suggested this is something we might like to do and sort of really guide us with the science behind it. Fundamentally, what they're trying to do is, given a molecule or a structure, is trying to work out how it's likely to perform. So in terms of drug discovery, how toxic is it? How soluble is it going to be? How active it's going to be against what you're interested in? And a standard way of doing that, I suppose, is to get a sample of this, take it to a lab and actually do the experiment. But when you've got thousands of things you want to screen, which are very expensive to buy, if you can buy them at all, that's a difficult process. And also, if you're doing things like toxicity, you want to minimize the number of experiments you do because there's some sort of ethical constraints in there as well. So what they do is use a technology called QSAR, or Quantitative Structure Activity Relationship. And what that says is the properties of your molecule are somehow related to the shape of it or the structure. It's attributes like the length of it or the number of certain types of atoms or whatever. Usually in terms of numerical things you can work out for a structure, you can use that to relate that to the properties. We looked recently, there's sort of 3,000 things about that you can measure or work out for a particular structure. So there's lots of information you can take about this and use that to relate that to the properties that you're interested in. There's a lot of data around as well to help you do that. We use 3 databases, Kemble, Wombat, and Wombat PK, a sort of pharmacokinetic database. The Kemble one, for example, has 600,000 compounds, and it was actually taken from 34,000 publications that a set of students in East Europe, I believe, were paid to just type in these things into databases. Wombat PK, there's lots of clinical measurements in there as well, which is very useful. And in the database, what we're interested in is structural information, so the shape of these things, and the numerical activity values. So the problem becomes, what's the relationship between those two things? How do you relate structure to the activity? So QSAR is really just a regression exercise, really. And it goes through a standard process where you take the data, you build your models, you'll validate them on unseen data, and then you use those models to predict structures you haven't seen before. So what you would do to build a set of these models is pick a compound list similar to what you're interested in. You select from those 3,000 predictors ones you want to calculate. So you'll work all those out. Because you've taken the data from one of these databases, you actually know what the activities really were. So that gives you a set of X data and a set of Y data in terms of modeling. And then you can relate those two things together. The problems are, well, which compounds do you pick to build the models on? Of those 3,000 descriptors, what do you want to calculate? And also, there's any number of different modeling techniques you can use. So which one do you actually want to have a look at? So given a model, the next set is to actually see how that works on data it wasn't trained on. So you'll pick another set of compounds, again, probably similar, calculate the same set of descriptors, and use that model to give you an estimate of the thing you're interested in. Again, you know the actual, so then you can work out what your error was. So then, if that model's acceptable, you can then use that with structures you haven't seen before to give an estimate of the properties you're interested in. So what they do in Newcastle is to screen big libraries of compounds using these things to try and pick out ones that are worth investigating further. So they use these models and sort of screen thousands and say, of these thousands, these ones are the ones I'm going to look at. And what we did with the junior project is to try and model all the data we could find and make it available on our website. It's called openqsar.com. It may or may not be running at the moment. I hope to demo it later, but we'll see. The problem with this QSAR process is that there's a lot of choices you have to make all the way through it. Sort of which descriptors you're going to pick, what models you want to build, how you're going to test them. And the quality of the models you get, it really depends on getting these choices right. But it's always different, so different properties will have different models that predict them well. I'd say the junior project aimed to model all the public data we could find, but we used a system that the cancer research people had called Discovery Bus. And what that does is it applies all the modeling techniques you show it to all the data, so it's a huge system that tracks the process of building these models. So, to discuss this a bit, the standard process is that you get training test data, calculate descriptors, and build the model. But with all the choices you have, there's different ways of splitting the data. There's different descriptor calculators you can use. How you pick those is also an open question, so there's lots of different ways of selecting which ones you're going to use. And then the different models you use. So you get a lot of information that needs to be managed in the process of building these models. And Discovery Bus sort of coordinates all of this. It's an old system. It's been around since the sort of late 90s. It was built with Oracle. It uses stored procedures to do most of its logic. It's horrible to maintain and look at. Models built in R, which is a sort of open source statistical language. We also do some models in Java. And the system's meant to scale by having multiple agents that can do this modeling work. One of the attributes of Discovery Bus is it's always active. So once you start it off, a modeling process is never truly finished. Because if you add a new set of data to it, a new descriptor calculator or a new model, it'll go back and update the results for that new data. So it's always sitting there running. And the idea behind it was to connect it to sort of a company's sort of compound database. And every time you add more data to it, it would automatically rebuild models. As I say, it's very hard to maintain. There's no documentation to speak of. And it's very specific in what operating systems and libraries it uses. So we've managed to get it running on Amazon using a specific version of CentOS. Just about sits there running now. So what we want to do to extend that is to make use of Windows Azure to provide more resources to that. Also add different types of agents, different modeling routines, and try and move it towards something that's more maintainable and a bit more modern. Having said that, it does a lot of useful stuff. So this is the workflow Discovery Bus uses when it builds a model. It's quite hard to see, but there's two steps. Your discovery, model building, and validation. That breaks down into different parts as well, so it's a multi-level plan. And there's a lot of bits of information that are passed around and tracked, so it's not something we want to really implement again if we can get away with it. The way we extend it, it's built around something called a bus master, which is one machine that coordinates the whole process. So this is all data, and that's the Oracle database there. Other machines connect to this, and occasionally they'll query this. Is there anything that needs to be calculated? So they're forever polling this master, pulling out work to do. There's another agent which continuously looks at all the models you have, all the data sets, and works out if there's anything that needs to be done. And what we did is sort of fake one of these agents. We called it a proxy agent. It looks to Discovery Bus like everything else, but what it does is it sends the work that it does out to our worker roles in Windows Azure. And we scale by having that proxy agent pretend to be lots of agents. So our initial results, first we start with 2 workers. So 2 of those proxy agents did our set of data in just over an hour. Again, up to 10, we've got to speed up. So what you see here is a sort of computation-intensive bit where you're building those descriptors and calculating the models. And then it goes on to a kind of admin and validation stage. So 20 workers, so it squeezes up our calculation bit of it. We still have that same tail at the end. And that was our problem, really. We could only really scale as far as 20 workers, which isn't very good. The problem is really that this huge, great tail on the end of it, after you've done the computation expensive bit, where it's validating and checking models, doesn't scale very well because it's focused on the database aspect of things. So a lot of that is based on Oracle store procedures, which don't go out to Azure at all. So that gives this huge long tail that we don't get any further with making it better. So after a lot of testing, it basically comes down to the fact that it's all built around one database. There's a single point in the middle that everything has to go through. So the obvious thing we did was try and optimize that. It was running originally on just a standard Amazon VM, so we bought the biggest, fastest machine we could get for it. The data was stored what's called an EBS, a block store, which is effectively a network drive, so we moved that onto the node itself, which helped us. We used sort of standard things like NFS to move files around because it was using a single-threaded file transfer, which didn't help. And also trying to optimize the store procedures, something we really didn't want to have to do. So we got it down to taking about a second for it to work out that there was some new job that needed to do, which gave us a kind of a limit, really. We couldn't generate models more than 1 a second. So that's as fast as our system could go. And that's really the limitation of Discovery Bus being always active and always doing a lot of work in the background to work out what's needed to be done next. So we did things like trying to simplify the model plans and everything, and we got down to scaling to about 40 to 50 nodes. And this is the result of that. Before our optimization, we had that biker CPU and then the long tail. So that's 19 Azure nodes taking 2.5 hours. Afterwards, 1.5 hours and about 15. So we've got much better utilization. Probably as good as we're going to get with this. So having done that, we went ahead and built all the models and put them on a QSAR. And I'll try and show you that now. So this is the site. If you look at the properties, so fingers crossed. These are all the properties we modeled. The type of thing here, so IC50 is a measure of how well it actually works against something. So for this one at the bottom, we've got 25 models. So I go into one of those. Of those, a bit of information about its training performance, its testing performance. We will be able to get predictions. We can't yet. So you'll be able to paste in a structural set of structures and have it actually give you the estimated properties from that. That doesn't work yet, unfortunately. But if you look at one of these models, this is its performance on the training data. It's a bit weird. And the testing data there. And also the descriptors that are actually picked for that model. So out of the thousands, it's picked those of 10 descriptors or so there. So that's the site we're building. At the moment, we've got sort of 240,000 models on there. It's at openqsar.com, although that address doesn't look like that at the moment. And it's going to be available for people to get predictions and hopefully download that data as well and use it in other places. So, having done that, we went back and tried to analyze how poorly it scaled. So we ran tests on sort of 2, 5, 10, 20 nodes. And what we tried to do is compare the numbers of models we got out per minute. So each data set we put in will generate about 80 models, and they're called responses, so in Discovery Bus terminology. So we just try to do a graph of throughput against system size, if you like. It was expensive to do because we got to the point where we weren't getting Azure nodes for free anymore, so we had to pay for all of those. So we only did it once. So we didn't do multiple runs of each. So we did 1 at 2, 1 at 5. I'd like to see half a dozen at 2 to see the kind of spread of speed you got, because we certainly found that we get a lot of variability in how things work depending on what time you ran it on and how busy other machines were. So we didn't get the best sort of process for benchmarking it, but this is what we found, is that initially it scales fairly well, and as we hit the limit of the database at about 40 worker nodes, it just sort of dies then. And in a conference where people are talking in terabytes and petabytes and gigabytes and thousands of nodes, to come and give the number 40 is a bit embarrassing, but there you go. It's what you get when you just dump something naively on the cloud, really. Which comes to what we want to do next. We got it running on the cloud, but we really didn't make use of a lot of the components that are there that would have probably helped us. So if we made use of queues, blob storage and table storage instead of the SQL database, we can probably get a lot better sort of utilization of resources and really try and move all this coordination away from our central database and distribute some of the coordination around the components in the workflow. So once you've done something like calculate descriptors, using a step in the workflow, that part will be responsible for kicking off the next part. So you move logic out of the database onto the queues and sort of distribute it around, and just use a database for storing results at the end of it. We're involved in a European project, Venus C, also with Microsoft, and what that's trying to do is put sort of a generic interface on different clouds. So what we want to do, and we're one of the use cases in that, is to make use of our time to actually try and re-implement the discovery bus to make use of this API and see if we can scale above sort of 40 and 50 nodes. So to sum up, moving it to the cloud really exposes weaknesses in your architecture. I mean, we didn't do that well with sort of dumping 100 times additional resource onto the system. So we're going to need to change our architecture to go further, and I'm sure that's the case in a lot of situations where you just put it there and it exposes problems straight away. But we have generated a lot of models, and they're available for people to use, and we've been able to take this resource, use it, and switch it off. So it was very useful, and it did what it's supposed to do, and we can easily switch it back on again and do it again. And we only really paid for 4 weeks of compute time, so it wasn't bad at all. And it should be the ideal cloud application that it's bursty, because once you get certain data, you need to do a lot of work. It's very easy to parallelize, because all those models are independent, so you can just run them separately. So, well, that's about it. Thanks.
Questions for Hugo? We got two over here. We'll let Jeremy go first.
I was just curious, so your peak at 40,
Yes.
Was that due to the problems of the actual database application?
Yeah, we just hit 100% CPU on the database. We had the biggest sort of Amazon machine we could have with multiple CPUs, and we couldn't physically run it on a bigger machine. So that was just down to the, once we had that much data in there, the queries slowed down. It just got bogged down, really, unfortunately. So given our architecture, that's probably as far as it will go.
Okay. And that was the same on Azure?
Yeah, I mean, if you look at the original graph, the proxies were all running in Amazon, so it looked to the database as if they were just more Amazon resource. So it wasn't a communication to Azure, because file size was a few K. I don't think it's the difference between the two clouds. I think it's just the architecture of the database.
Okay.
Once it was in Azure, it was nice and quick.
The real difficulties in doing the modeling
Yeah.
is choosing the data, choosing your sets.
Yeah.
One of the dangers of letting it just keep running is that effectively the test set becomes part of the design set and the whole thing
yes,
falls
it just
down.
ends up learning on it. Yeah.
So it's also, I'm not quite clear what's the automatic thing. It's somebody says, I've got this particular test set, or I've got this data.
Yeah.
I mean, does it decide on the model it's going to do? I mean, not the modeling. What actual problem is trying to be solved?
It's one of the things you tell it at the beginning. So you'll give it a data set and say, I'm trying to model this property with these things. And it will go and apply all the models. It'll do sort of leave one out validation and do sort of sensible partitioning of data. But it's basically a sledgehammer that just goes and smashes away at it and formats the results and orders them so you can pick them. So it doesn't have any intelligence really.
Okay, so and then if you come along, so you just basically keep coming on and say, I've got a new problem here.
Yes.
It just gives you all the options back. Okay.
Yeah, and it'll sort them or rank them in terms of correlations and things that you want to make.
So one of my concerns, I'd forgotten that the basic system was there for so long, but obviously you've got to have the computer power to run all these things.
Yeah.
So it runs and all the data comes back, and it looks like a black box to the users.
Yeah.
Now, currently, most of the people who build those models have to know really quite a lot about the models to not get trapped. Is there the black box danger going to turn up?
It is. It's not popular with people that do QSAR because it kind of takes away some of the black magic of it. But it's like any black box. You need to interpret it and be careful how you use it. My background's in chemical engineering and modeling chemical processes on a larger scale. But once you've got a model, you've got to be careful to use it in the range you trained it on and be very aware that it doesn't extrapolate well.
Yeah.
And it's the same problems there as well. It just gives you that range that you can pick things from. So,
Other questions for Hugo?
Hi, yeah, it's a great application. I was just, essentially you're just hitting Amdahl's law with the parallelization, right?
Yeah.
Because your database is fundamentally a sequential process, and therefore you're always going to limit your scalability. So the only thing to do is to
re-architect.
Yeah, which is a pain. But
well, it is, but it's also an opportunity, isn't it? We've got this kind of couple of years project to do it. We may as well tackle it and see what we do.
Yeah. Yeah.
It's going to be the same problem. However, we have a centralized resource there at the middle, we're going to get that contention. So unless we distribute it, we're going to hit a limit sooner than we'd like anyway.
Yeah, because I think that's good in terms of patterns and practices for cloud computing. That's a lesson that people who aren't experienced in HPC might sort of forget. So.
You hit really quickly and disappointingly so sometimes.
It's good. You could use that in teaching parallel computing, I think, as an example.
Any other questions?
OpenQSAR.com. Yeah, I know, it doesn't... Yes, I don't know what's wrong with that. It's on Amazon, so it might have the wrong IP address set of it.
Forgot to pay your bill on your domain name registration.
It's very bizarre. Yeah.
But as soon as the guy back in England has fixed the DNS,
well, we are going to point out to him that it's quite embarrassing, and I hope he does it fairly soon. But yeah, it will be there definitely.
All right.
It's not, it really isn't. I mean, it could have been so much worse, but.
It's time for lunch. Let's give a final round of applause to both Mark and to Hugo this morning. Thank you.